So go ahead.
Great. Okay. Fantastic. Thanks, everybody. I'll try to go quickly because I know I'm the last one here between you all and lunch. So if I could have the next slide, please. Right. So the thing that strikes me about the near-Earth object question is it really boils down to a couple of things. We'd like to know when the next impact of any substance will occur and how bad will it be. And so that kind of sets the tone for what we're going to propose to do next. The when comes from just finding the objects and figuring out good enough orbits about them that we can tell when they might have a potential impact with the Earth. And the how bad part is basically a question of getting some estimate of the impact energy, which of course scales as the kinetic energy, 1/2 mass times velocity squared. So of course you get the velocity from the orbit. So if we found the object and gotten a good enough orbit to predict an impact, we know the velocity. And the mass, of course, roughly scales as the density times the diameter cubed. So that says that the impact energy is strongly dependent on the size of the object, its diameter. And of course, when we talk about diameter, we mean effective spherical diameter here. Just in terms of getting the broad brush on the impact energy, that is sort of the 0th order question, parameter of interest. Okay, if we go to the next slide, now we might consider how do we go about doing this in the most effective way. And that comes from looking at asteroid spectral energy distributions. If we just plot up a couple of SEDs of typical near-Earth objects, in this case I've shown here a 140-meter NEO, it's about 1 AU distance away from the observer and located at 90 degrees solar elongation with a couple of different representative albedos, you can see that most of the energy is actually coming out in the thermal infrared. Asteroids are fairly dark, gray, or very, very dark, and they just don't reflect a lot of visible light. So I've highlighted a couple of band passes of interest because these are two wavelengths that we think are particularly useful for finding the objects where they're naturally very, very bright. So why do we look in the infrared? Because that's where the light is. It's kind of like the old saying about why does a guy rob banks? Well, that's where the money is. So in this case, we want to go where the photons are for these objects. May I have the next slide? And just to drive the point home a little bit, asteroids are bright in the infrared, and stars are actually less so at similar sensitivities and depth. And what I'm showing here are a couple of objects. These are actually main belt asteroids, but the point holds. You can see the color coding is, the cyan is 3.4 microns, and going outward in wavelengths to 12 and 22, you can see that there's just very little in this image, which is a very typical part of the sky. There's almost nothing here that's yellow and orange. The stars are mostly blue, and the asteroids pop out brightly. Another aspect of this is not only are the asteroids bright in the infrared, but the stars are suppressed. They just are much warmer. They're thousands of kelvins, so most of their energy is peaking in visible to near infrared light. So asteroids are bright in these wavelengths, stars less so. So there's more contrast and less confusion. Next slide, please. And when we look at the distribution of near-Earth object albedos, we know that there is a population of objects that are extremely dark. And the new results from OSIRIS-REx and Hayabusa 2 are really interesting because they drive home the point that some near-Earth objects, a non-negligible fraction of the population, are just incredibly dark. They're very, very primitive carbonaceous objects, and they're out there in fairly sizable numbers. And so it's important to find them. So when we talk about finding objects down to a certain size, it's important to consider the low albedo population as well. Next slide, please. So what we've done is, with NEOCam, tried to design a mission that really is optimized for addressing the questions of when the next impact will be and how bad is it likely to be. And we call it NEOCam, or the Near Earth Object Camera. It's designed to respond to the Planetary Defense Coordination Office's needs for tracking, discovering, characterizing NEOs. And this is its sole purpose. It's not trying to do any other science. So because of this, it can really be truly optimized for going off and finding these objects as well as characterizing them. And that allows us to provide decision support for anybody who has to be involved with the decision of whether or not to engage in some sort of mitigation campaign should the need arise. And it can inform you as to the best possible strategies for mitigation. So next slide. So just a quick picture of it. It looks sort of like a mashup of Spitzer and Kepler with a little bit of WISE thrown in. The instrument is painted a very dark black, which allows it to radiate heat into space. and the front-facing side of it is a solar shield and solar panel combination, just very much like Spitzer. The difference is the sunshade is a lot taller, and what this allows us to do is turn the telescope so that it can look fairly close to the sun, because that's where a lot of the hazardous asteroids are scattered around the Earth's orbit. So we want to really be able to survey the volume of space all around the Earth's orbit. And to do this, we have a two-channel imager using those two wavelengths that I highlighted on the first slide at about 4.5 and 8 microns. And we would just operate this in a step and stare mode, doing the same pattern over and over and over again to find any nodes. Next. It's a 50-centimeter telescope. Next, we'll just fly through these really fast if you can just please flip through them. And the idea is to use some very up-to-date detectors, because of course the cell phone camera revolution has even reached into the infrared at this point. And so we would send this telescope out with two 16-megapixel Mercad telluride focal planes that can image both channels simultaneously with a beam splitter. Next. And the idea is to passively cool this observatory. So instead of keeping it in Earth orbit, because the Earth is hot, we would actually send it out to the Sun-Earth L1 Lagrange point, where it's just far enough away to get away from the heat load of the Earth, but it's close enough and it stays at a constant enough distance that we can reliably get the images back with a very high data rate. So it's had a long track record here. It was first proposed through the NASA Discovery Program in 2005. In 2011, we were awarded technology development funding, which we've used to work on our detectors. Next. And at this point, we were awarded extended phase A in 2016 in the Step 2 Discovery round there. And since then, we've had a couple of big reviews. Next. And next. And so, yeah, where we're at now, we're at the point of being in preparation for our key decision point B review. So we've just passed our pre-KDPB review with our review team, and we're getting ready for the actual key decision point B review for the instrument, which hopefully will come up this spring. The shutdown did delay things a little bit, but we're raring to go and back on track. So next slide. And of course, in terms of productivity, this survey should be very productive at finding a large quantity of the potentially hazardous asteroids, or PHAs, that are larger than 140 meters. This is from NASA's Science Definition Team report that was published in 2017. And it considered a variety of different mission architectures, including ground-based telescopes, visible orbiting telescopes, as well as infrared. And again, just to kind of come back to the point, the reason we look in these wavelengths is because the asteroids are just naturally very bright there. So you don't need as large an aperture to capture such a large fraction of the light and be very sensitive. Next slide. So the mission objectives are pretty straightforward. It's to find at least 2/3 of the PHAs larger than 140 meters in 5 years, with a goal of reaching that 90% objective from the George E. Brown law that directs NASA to go undertake this survey. We would produce diameters and compute albedos if we have archival visible light data. And we would calculate the cumulative chances of impact over the next century from objects as small as 50 meters and up, as well as comets. And the idea is to adhere to the standard NASA data delivery practices. We'll be delivering tracklet data, so positions times fluxes daily, and then the actual images and extracted source lists and infrared sky atlases would follow every 6 months into the public archives. So very similar to what we're doing now with NEOWISE. Next. Cadence, again, this is a mission that is optimized for finding NEOs. What we need is a cadence that allows us to find them and reliably distinguish them from main belt asteroids or more distant objects. So most of our objects are detected over and over and over again in multiple epochs spanning either months or years. But in spite of this extremely repetitive survey cadence, we are preserving the capability to stop and point at a specific target of interest should the need arise. So for example, if we find an NEO that looks like it's got a particularly high probability of impact at some point in the near future, but it's at 45 degrees solar elongation and it's an equivalent V magnitude of about 25, we can actually stop the survey and point the telescope at this object and just sit on it for as long as we like to collect light curves, deeper observations in both channels, and just build up coverage at multiple phase angles so that we learn more about its physical properties, rotational shape, rotational state and shape, and thermal inertia, for example. And the idea is to carry out, other than that targeted mode, the idea would be to carry out this extremely repetitive survey cadence, which operates on a 2-week cycle roughly, flipping back and forth on either side of the sun, like I said, over and over again for the entire duration of the mission. Next. Thank you. So in terms of, pardon me, in terms of technical progress throughout this extended phase A that we've been in for the past couple of years, we've been very busy manufacturing our sensor chip assemblies. We're now able to manufacture long wavelength detectors in a 2048 by 2048 monolithic format, very similar to their shorter wavelength cousins. We've been growing multiple lots of both 5 and 10 micron and longer devices, and have completed a fair amount of radiation and environmental testing on these channels, on these chips. And of course, we're in the process of constructing our engineering unit camera enclosure assembly so that we can verify the heat loads that we expect, so that we can validate the passive cooling that we expect to do with NEOCam. And we've been very busy prototyping elements of the NEOCam science data processing pipeline so that we can reliably extract the object detections out of this very large data stream that we anticipate. So that includes things like constructing simulated images, working on image differencing and machine learning and assisted automated classification quality assurance, and then doing some trackward linking simulations. So that work is ongoing. Next slide, please. And this is just a photo of some of the detectors. The focal plane module for one of the channels is shown there on the left. It's about the size of your cell phone with all of the 4 chips stacked up together. We go with this elongated format because it allows us to step between fields in the most efficient way. And you can see a picture there on the right of some of the tape cables coming off of the focal plane module assembly in our engineering unit that we're working on. So that's been a very profitable partnership between Teledyne, University of Rochester, and JPL over the years. Next. And you can just flip through these next bullets here. Thank you. So I've already said this. Anyway, yeah, so the detector testing has gone really well. We're very happy with how it's come out. And these devices have very low dark current, and they've been through quite a bit of radiation testing now. So next. And there's some of the papers. Next slide, please. And that's all I've got. I think that's it. So thank you. We're really looking forward to continuing work on NEOCam and getting through the next steps. Thank you.
Thank you, Amy. Time for 1 or 2 quick questions.
I'll ask a question, Tim. What is SBAG standing on proceeding with NEOCam?
The question is, what is SBAG standing on proceeding with NEOCam? I think that might have been a plant. It wasn't. No, it actually wasn't a plant, but SBAG has. Interested
scientist who is not affiliated with NEOCam.
From an interested scientist who is not affiliated with NEOCam, Rick Benzel. But SBAG has consistently found in favor of infrared, space-based infrared surveys, and more recently in NEOCam in particular. And so comments are welcome on that. That has been the consistent stance.
I guess I just would like to jump in and say, you know, this is a field, this whole field of planetary defense, it's an important question. It's a question we can actually really do something about with a really fairly modest amount of effort on a big picture scale. And so I think it's a field worthy of study and a problem worth solving.
Yeah. And we do have one question.
This is from Joel Marks, who asked, our luck has held up since 2005. Any thoughts on how to speed up PD funding?
Did you hear the question?
Yes. Well, you know, again, as I said, this is an important problem, and I think all the attention that this has gotten over the years is all to the good. And we all think that small bodies are important. We know that they interact with the Earth. We'd really like to understand how often that occurs on our lifetimes and in our time scales as opposed to geological time scales. So I think just generally raising the profile of this field is an important thing to do to make everybody aware, the public, congressional leadership, stakeholders, NASA, all the rest. This is an important problem, and you know, getting that message out that we can do something about it, I think, is really good.
Okay, thank you very much, Amy. So that concludes the morning session. We will reconvene at 1:30 with Rick Benzel.